I'm Shota Yamanaka from Yahoo Japan Research. In this study, we investigated performance models on lassoing time to select multiple objects. We can use some methods to select multiple objects, like rectangle selection, multiple taps, and lasso selection. And more efficient techniques have been proposed. Generally, researchers measure the operation time as the efficiency of a proposed technique, and also they measure the times of baseline techniques for comparison. We can predict operation times of a rectangle selection and multiple taps by using Fitts law. But lasso selection is too complicated to derive a good model to predict operation times. Lasso operations are used to select multiple objects on illustration software, note-taking tools, and presentation tools. When users draw a complicated stroke, they have to carefully move the stylus through objects. But how do users decide the movement speed depending on the task conditions? In this study, we used arbitrarily shaped objects to investigate the relationship between task conditions and task completion time. This is a subsequent work of our KAI 2019 paper. In that study, we used only square icons that formed constant width paths. So the best strategy was keeping a constant speed. The results showed that segmenting a path into small portions to apply performance models was efficient to predict movement times. In contrast, in the current study, we would like to predict the movement time when the path width changes during making a stroke. In realistic scenarios, users have to go through several steps, such as deciding which objects to select, determining a path to select them, and pointing to the start position. As we aim to model the time required for the main lassoing operations, the time needed for these steps are out of scope for the current study. Therefore, in our experiments, the desired objects are highlighted in orange, the movement direction is fixed, and the start position is given. Next, let me explain about the experiment 1. The objects were made by PowerPoint shapes, and we overlaid the white path to be steered. Participants make a stroke in clockwise direction from the blue start area as quickly and accurately as possible. They cannot touch any objects. When the cursor touched a green or orange object, the participant had to repeat the trial from the start position. We used 3 path shapes, including constant width, narrowing, and widening path. The path shape was determined by the path parameters of W1 and W2. In the constant width condition, the participants could keep the movement speed, but in narrowing and widening conditions, they had to dynamically change the speed based on the current path width. There were 54 path configurations, and they repeatedly tried 5 blocks. To see how the participants performed the task, we analyzed the speed profiles. This is the result of the constant width path for the first 3 path segments. As the path width increased, the participants exhibited a higher speed because they paid less attention to the path boundaries. In addition, because they turned a corner between segment 3 and segment 4, they began to decelerate in the earlier phase during segment 2. Next is the result of the narrowing path. Because the path width decreased in segment 2, the speed decreased in this area. However, for the green and orange speed profiles, the path width at the beginning of segment 2 was the same, 20 mm. But the speeds were different by approximately 15%. The participants seemed to begin adjusting to a speed appropriate for W2 even before the start of segment 2. Last is the widening path conditions. The orange speed profile shows that the speed gradually increased in segment 2. However, for the blue speed profile, the participants began to decelerate in segment 2, although the path end width was the same 20 mm. This was because the length of segment 3 was shorter for the blue speed profile. So the participants changed their behaviors by anticipating the future path and future corner. Next, we compare 4 candidate models. First, apply the global steering law model, which regards the lasso operation as a single steering motion. For a straight path segment, the index of difficulty ID of the steering law is A over W, where A is the path length and W is the width. For narrowing and widening path segments, the ID formulations are a bit more complex. Model number 1 is a simple formulation with only one intercept and one slope multiplied by the sum of ID values. Another approach is to use different slopes or intercepts for each path shape. According to our previous study, the slope and intercept values differ among these 3 path shapes. Therefore, there are 3 possible formulations, whether using different slopes, using different intercepts, and using both different slopes and intercepts. This is a comparison of the 4 model candidates. We used adjusted R-squared and AICC values for the indicators of model accuracy. First, the global model of the steering law shows a good fit. The R-squared value is 0.944, but using different slopes or intercepts significantly improved the model fits. This result showed that careful segmentation of a lassoing task into each path shape can improve the prediction accuracy of movement times. We also tested adding a fits law term for turning corners, but the model fits were not improved according to the AICC values. Next, in experiment 2, we tested the effects of stepwise path width changes. For example, in a widening path configuration, segment 1 was very narrow, segment 3 is a wide unconstrained area, and segment 2 is a transition area. We didn't test a constant width condition in experiment 2, and thus we used 2 path shapes, including narrowing and widening path. There were 32 path configurations, and the participants repeatedly tried 6 blocks. This is a result of the narrowing path for the first 4 segments. We show the speed profiles under different W3 values of the transition area. The result shows that the speed in the unconstrained area changed depending on the path width of the next transition area. We can see that the participants began decelerating in the middle of unconstrained area to safely enter the transition area. So the speed is not determined only by the current path width. It depends also on how narrow the future path is. Also, for the widening path configurations, the participants changed their behaviors in the unconstrained area depending on the path width of the transition area. The speed in the transition area was strongly restricted by the path width. Therefore, when the path width of the transition area was wide, the participants had to rapidly decelerate in the next unconstrained area to safely enter the next segment 4. In contrast, when the path width of the transition area was narrow, the speed at the beginning of the unconstrained area was not high, and thus the participants performed a slightly moderate deceleration. So in these stepwise narrowing and widening path shapes, the participants changed their speeds depending on the path width of the transition area, which also affected the speed in the unconstrained area. Next, we compare 4 models. First is to model a lasso operation as a single steering motion. This is the same model as in experiment 1. Model number 2 is to use a crossing row ID for the unconstrained area, because a careful steering operation is not needed in such a very wide area. Moving the cursor from a very wide area to a narrow area can be modeled by the crossing row model, which is the same formulation of Fitts law. Model number 3 is to use the crossing row model to segment 2 and segment 3 if the transition area is short. The final model number 4 is to approximate the transition area as a narrowing or widening path. This model assumes that the speed changes more gradually in the transition area, which reflects the actual speed changes as we observed in the speed profiles. This is a comparison of the 4 model candidates. Our hypothesis was that replacing the steering ID with crossing ID in the unconstrained and transition areas improves the model fits. However, this hypothesis was not supported. Moreover, model number 3 showed the significantly worse fit than the baseline model number 1. The best model was number 4, which approximates the transition areas as narrowing or widening path shapes. So in the transition areas, the participants gradually changed their speeds between the constrained and unconstrained areas, which was not a complete steering motion or crossing motion. Our intended task was to circle multiple objects via lasso-selection mode, but the models can be applied to other tasks. For example, activating commands and switching triggers are common tasks in graphical user interfaces, but clicking every target is time-consuming. Therefore, there are various techniques to enable such operations by drawing a single stroke. In these techniques, users pass through only an intended path. If they accidentally touched unwanted objects, they had to remove these objects or activate undo commands. According to our results, the movement time can be predicted by the steering row model with some modifications. This helps designing user experiments and interfaces. For example, when researchers evaluate new interfaces, they can estimate the potential decrease in task difficulty when the target size and offsets change. In this study, we tested only horizontal and vertical movement angles. However, in realistic lasso tasks, users have to move the cursor along more complicated paths. The movement time will be significantly affected by other factors. For example, previous studies have shown that diagonal paths and sharp curves took longer movement times. Because refined models were derived, we assume that the movement times can be predicted even for those complicated lasso tasks. We plan to evaluate such conditions in the future. The results supported our hypothesis that path-segmentation is an efficient approach for movement time prediction. But the movement speed was not affected only by the current path width, because the participants anticipated a future path segment. Based on our results, researchers can more accurately predict the performance of their lasso techniques and command selection techniques under new task conditions. That's all. Thank you for listening.